Good evening, and welcome to Cozy Sleep Time. Get comfortable and take a slow breath. Let your body relax more and more. Tonight's story is about the Northern Lights. Simply listen, or let your mind drift. There is no need to focus. Let the quiet story begin. Tonight, we explore the Northern Lights, one of the most beautiful phenomena in the natural world. Known scientifically as the aurora borealis, these lights appear as shimmering curtains of green, pink, purple, and red that dance across the night sky in polar regions. For thousands of years, humans have watched these lights with wonder, creating stories and myths to explain their presence. The scientific explanation begins with the sun, which constantly emits a stream of charged particles called the solar wind. This solar wind travels through space at speeds of several hundred kilometers per second, carrying particles and magnetic fields across the solar system. When these particles reach Earth, most of them are deflected by our planet's magnetic field, which acts as an invisible shield. But at the north and south poles, the magnetic field lines curve inward, creating funnels that guide some of these particles down into the upper atmosphere. As the charged particles enter the atmosphere, they collide with atoms and molecules of oxygen and nitrogen. These collisions transfer energy to the atmospheric atoms, exciting them to a higher energy state. When the excited atoms return to their normal state, they release the extra energy in the form of light. This process is similar to how a neon sign glows when electricity passes through the gas inside it. Each type of atom and molecule produces a different color when it is excited by the incoming particles. Oxygen atoms produce green and red light, while nitrogen molecules produce blue and purple light. The particular color that appears depends on the type of gas and the altitude at which the collision occurs. The lights take many forms, from gentle arcs that stretch across the sky to dramatic curtains that ripple and wave. Sometimes the aurora appears as a diffuse glow, while other times it forms distinct rays that seem to reach upward. On rare occasions, the aurora forms a corona, a crown of light that appears to radiate from a single point overhead. The intensity and frequency of auroral displays follow the sun's activity cycle, which lasts approximately 11 years. During periods of high solar activity, the sun releases more particles, and the auroras become brighter and more frequent. The aurora borealis has a southern counterpart called the aurora australis, which appears around the South Pole. Both the northern and southern lights occur simultaneously, mirroring each other across the planet. The human experience of watching the aurora has changed over the centuries, but the sense of wonder remains the same. We now understand the physical processes that create the lights, yet their beauty still inspires awe. The aurora connects us to the sun and to the larger universe, reminding us that we live within a vast and dynamic cosmos. The sun is the source of all auroral activity, a star that is far more dynamic than its steady light suggests. Our star is a massive ball of hydrogen and helium, held together by its own gravity and powered by nuclear fusion at its core. The sun's outer atmosphere, called the corona, extends millions of kilometers into space and reaches temperatures of millions of degrees. This corona is where the solar wind originates, as the sun's magnetic field accelerates charged particles away from its surface. Every second, the sun releases about 1 million tons of material into space through the solar wind. This constant outflow of particles travels through the solar system, carrying the sun's magnetic field with it. The solar wind takes about 3 to 4 days to reach Earth, traveling at speeds of 300 to 800 kilometers per second. The sun's magnetic field reverses polarity approximately every 11 years, at the peak of each solar cycle. During this reversal, the north and south magnetic poles of the sun swap places, and the magnetic field becomes more chaotic. This period of magnetic reversal is associated with increased solar activity and more frequent coronal mass ejections. On the sun's surface, darker regions called sunspots mark areas of intense magnetic activity. The number of sunspots rises and falls in an 11-year cycle, known as the solar cycle. During solar maximum, when sunspots are most numerous, the sun is more active and auroras are more frequent. During solar minimum, when sunspots are few, the sun is quieter and auroral displays are less common. Solar flares are sudden, intense bursts of radiation that erupt from active regions on the sun's surface. These flares release enormous amounts of energy, equivalent to billions of nuclear bombs, in a matter of minutes. Coronal mass ejections are even more powerful, releasing billions of tons of magnetized plasma into space. When a coronal mass ejection reaches Earth, it can compress our planet's magnetic field and trigger a geomagnetic storm. These storms produce the most spectacular auroral displays, with lights visible much farther from the poles than usual. The most powerful geomagnetic storm in recorded history occurred in 1859, known as the Carrington event. During this event, auroras were visible as far south as Cuba, Mexico, and Hawaii. The storm also caused electrical currents in telegraph wires, setting some telegraph offices on fire. Today, scientists monitor the sun continuously using satellites and ground-based telescopes to track solar activity. Space weather forecasting has become increasingly important as our society depends on satellites and power grids. Geomagnetic storms can damage satellites, disrupt radio communications, and even cause power outages. The connection between the sun and Earth through the solar wind creates the conditions for every auroral display. The aurora is the visible link between our planet and the star that gives us light and life. Understanding the sun helps us predict when the most beautiful auroral displays will occur. The colors of the aurora create one of the most beautiful spectacles in the natural world, a palette of light that shifts and changes as the display unfolds. The most common color in auroral displays is green, a bright and vivid hue that dominates the night sky during active displays. Green auroras are produced by oxygen atoms located about 100 kilometers above the Earth's surface. When charged particles from the solar wind collide with these oxygen atoms, the atoms become excited and emit a characteristic green light. This green emission is so bright because oxygen atoms at this altitude are abundant, and the green wavelength is easily visible to the human eye. Red auroras are more rare and appear at higher altitudes, typically above 200 kilometers. At these heights, the atmosphere is extremely thin, and oxygen atoms are more widely spaced. The collisions at this altitude produce a deep red light that often appears as a faint glow above the brighter green curtains. Red auroras are less common because they require very energetic particles to reach such high altitudes. Purple and blue auroras are produced by nitrogen molecules, which are most abundant at lower altitudes in the atmosphere. When nitrogen molecules are struck by incoming particles, they emit light in the blue and violet range of the spectrum. These colors often appear at the lower edges of auroral curtains, creating a beautiful border of purple and blue. Pink auroras can also appear when nitrogen molecules are excited at higher altitudes, mixing with the red from oxygen. The variety of colors in an auroral display depends on the energy of the incoming solar particles and the composition of the atmosphere at different altitudes. High-energy particles can penetrate deeper into the atmosphere, producing colors at lower altitudes. Lower energy particles interact with atoms and molecules at higher altitudes, producing different colors. The altitude at which the collisions occur determines which color dominates the display. The human eye is most sensitive to green light, which is why green auroras appear the brightest to observers. Red and purple auroras are often faint to the naked eye, but can be captured clearly by camera sensors. Cameras can accumulate light over longer exposures, revealing colors and details that are invisible to human vision. The colors of the aurora can shift rapidly as the display evolves, with different hues appearing and disappearing in moments. During intense geomagnetic storms, all the colors of the aurora may appear simultaneously, creating a spectacular multicolored display. The different colors appear at different altitudes, creating a layered effect in the sky. Green appears at the lowest altitudes, red at the highest, and purple and blue in between. The science of auroral colors reveals the precise composition of the upper atmosphere and the energy of the particles that strike it. The northern lights are most commonly seen in a ring around the magnetic North Pole, a region known as the auroral zone. This zone lies at latitudes between 65 and 70 degrees north, circling the planet like a crown. Within this zone, the lights appear on most clear, dark nights, though their intensity varies with solar activity. The auroral zone passes through some of the most beautiful and remote places on Earth. In North America, the best viewing locations include Alaska, northern Canada, and Greenland. In Europe, the aurora is frequently visible in Iceland, Norway, Sweden, Finland, and northern Scotland. The Scandinavian countries offer some of the most accessible aurora viewing, with well-developed tourism infrastructure. Iceland has become one of the most popular destinations for aurora chasers from around the world. Russia's northern regions also lie within the auroral zone, though access is more limited for most travelers. The best time of year to see the northern lights is from late autumn to early spring, when nights are longest. In the northern hemisphere, the peak viewing months are September through March. The darkest months of December and January offer the most hours of potential viewing darkness. However, these months also bring the coldest temperatures and the most unpredictable weather. The hours around local midnight generally offer the best chance of seeing active auroral displays. Auroral activity tends to peak near midnight, though displays can occur at any time during the night. Clear skies are essential for viewing, as clouds block the aurora completely. Weather forecasts are important tools for aurora chasers, who need to find locations with minimal cloud cover. Darkness is equally important, and light pollution from cities can wash out all but the brightest auroral displays. The best viewing locations are far from urban areas, where the night sky is truly dark. The KP index measures geomagnetic activity on a scale from 0 to 9. Higher KP values indicate stronger geomagnetic storms and more extensive auroral displays. At KP 5 or higher, auroras may be visible at mid-latitudes, including the northern United States and Central Europe. At KP 7 or higher, auroras can sometimes be seen as far south as the southern United States. The aurora australis, the southern lights, appears around the South Pole in a similar auroral zone. The best place to see the southern lights is Antarctica, though New Zealand, Tasmania, and southern Chile also offer opportunities. Aurora forecasting apps and websites now provide real-time predictions based on solar wind data from satellites. These tools help travelers plan their trips and increase their chances of witnessing a spectacular display. The combination of preparation, patience, and good fortune creates the perfect conditions for viewing the aurora. Before science explained the aurora, cultures around the world created stories to make sense of the lights in the sky. These legends reflect the deep connection between human beings and the natural world, and the need to find meaning in celestial events. The Inuit people of North America traditionally believed that the aurora was the spirits of the dead playing a game with a walrus skull. Some Inuit groups saw the lights as the souls of children who had died at birth, dancing in the sky. Others believed the aurora was a path that guided souls to the afterlife, a bridge between the world of the living and the world of spirits. The Sami people of Scandinavia regarded the northern lights with great reverence and caution. They believed that the aurora could harm those who stared at it too long or mocked it. Sami children were taught not to whistle at the lights, for fear of attracting the attention of dangerous spirits. The lights were sometimes seen as the energy of souls, reflecting the Sami belief in the spiritual nature of the natural world. In Norse mythology, the aurora was associated with the Valkyries, the warrior maidens who chose which heroes would die in battle. The lights were thought to be reflections from the shields and armor of the Valkyries as they rode across the sky. Some European legends describe the aurora as a great fire in the north, reflecting the fires of distant lands. In medieval Europe, the aurora was often seen as an omen of war, famine, or other calamities. Red auroras were particularly feared, as they were thought to predict bloodshed or disaster. The Chinese recorded auroral observations as early as 2,000 years before the Common Era. Chinese chronicles describe the lights as dragons or celestial serpents moving across the sky. In some Chinese traditions, red auroras were seen as signs of important events or changes in leadership. Japanese folklore described the aurora as a sign of good fortune, with the colors representing different blessings. The Ainu people of northern Japan believed the aurora was the light of the gods, illuminating the path for spirits. Some Native American tribes of the Great Lakes region believed the aurora was the reflection of great fires in the north. Others thought the lights were the spirits of ancestors dancing and celebrating in the sky. Many cultures saw the aurora as a source of practical information, indicating weather changes or the movement of animals. The diversity of these stories shows how deeply the aurora has affected human consciousness across the globe. Modern science has replaced these ancient explanations with a physical understanding of the phenomenon. Yet the sense of wonder that inspired the old stories remains, and the aurora continues to fill observers with awe and curiosity. Earth's magnetic field is the invisible structure that shapes the aurora and protects our planet from the solar wind. This magnetic field is generated by the movement of molten iron and nickel in the Earth's outer core, thousands of kilometers beneath our feet. The movement of this liquid metal creates electric currents, which in turn produce a magnetic field that extends far into space. This field is similar to the field produced by a simple bar magnet, with a north pole and a south pole. Earth's magnetic poles are not aligned with the geographic poles, and they drift slowly over time. The magnetic North Pole is currently located in the Arctic Ocean, moving toward Russia at a rate of about 50 kilometers per year. The region of space dominated by Earth's magnetic field is called the magnetosphere. The magnetosphere extends hundreds of thousands of kilometers into space, acting as a shield against the solar wind. On the side facing the sun, the magnetosphere is compressed by the pressure of the solar wind. On the night side, the magnetosphere stretches out into a long tail that extends millions of kilometers away from Earth. This magnetotail contains trapped particles from the solar wind, stored until they are released during geomagnetic storms. When the solar wind is calm, the magnetosphere remains relatively stable and auroral activity is moderate. When a coronal mass ejection or a strong gust of solar wind arrives, the magnetosphere becomes compressed and disturbed. This disturbance accelerates particles trapped in the magnetotail, sending them streaming toward the poles along magnetic field lines. The particles follow the magnetic field lines down into the atmosphere, where they create the aurora. The shape of the magnetic field determines where the aurora appears, which is why auroral displays are concentrated around the magnetic poles. The magnetic field lines curve inward at the poles, creating funnels that guide particles into the atmosphere. Without Earth's magnetic field, the solar wind would strip away the atmosphere, as it did on Mars. The magnetosphere is not a perfect shield, and some particles always leak through, creating the constant background auroral activity. The boundary between the magnetosphere and the solar wind is called the magnetopause, and it shifts constantly with solar activity. During intense geomagnetic storms, the magnetopause can be pushed much closer to Earth, allowing particles to reach lower latitudes. The Van Allen radiation belts are regions of trapped charged particles within the magnetosphere, shaped by the magnetic field. These belts swell and contract in response to solar activity, sometimes affecting satellites that pass through them. The study of the magnetosphere helps scientists understand both the aurora and the broader relationship between Earth and the Sun. Earth's magnetic field is essential to life on our planet, and its interaction with the Sun creates the beautiful light show we call the aurora. As our story ends, let the quiet ideas settle softly. Your body can continue to relax, breathing slow and steady. If sleep is near, let it arrive naturally. Thank you for spending this moment here on Cozy Sleep Time. Return anytime for another peaceful journey. Good night.